Okay, everybody's going to live to 110, but nobody knows how to pay for it, so never mind. So we have to work till we are 90 then probably. Yeah, I hope not die. And so you can see there's a relation between the CO2 and the temperature, but here the relation is off a little bit. But it's a lot of philosophy that flows into that. And you have to, of course, not only look at one ice, but you have to look at different locations and so on and so on. So you see now, so how do you get that ratio? This is the whole point I'm trying to drive home here. How do you get that ratio? How do you do that? So you use a mass spectrometer. And the mass spectrometer is extremely sensitive. I explained it in a very simple way to you. It can, billions of a mass, it can determine the difference of billions of a mass. Okay. So what you have, you take your sample, and the sample is some kind of ice core, or is some kind of metal or whatever. And so this is neutral, it has no charge. So you take off an electron. It's called ionizing. If you take off an electron, you ionize it. And that means, what is now your atom? What is that now? It's positively charged. Okay. If you put an electron on it, that also can be done, not as easy. You put an extra electron, it's charged too, but then it's negatively charged. But we want to have it in this case, we ionize it, we rip off an electron. Okay. So we do this in a radio frequency coil here, we ionize it, and now you have a charged particle. Now we can accelerate it by putting an electric field on it, and that electric field is negative, so it accelerates that particle to a certain velocity, and we make that electric field so that it's like a hollow, that it can fly through there, and now it has it's accelerated, and masses that have charge and move in a magnet, they will be deflected. This is a relation of mass over charge, and the lighter they are, the more they will be deflected, the heavier they are, the less they will be deflected. So all I need now at the end to get these ratios, to analyze these compounds, all I need at the end is something, a sack where I have to hold it here, you go in that sack, you go in that sack, you go in that sack, okay? Like a bin, I bin it. And so then you have that many of that mass, that many of that mass, that many of that mass, and so on and so on. This is called a mass spectrum. And so now let's do that here. There's our sample. We're going to ionize it, and then we accelerate it, and now it deflects. And there, it gives us a signal. And the location of the signal tells you the mass, and the strength or the height of the signal, it tells you how many of those at that mass you have. That's all there is. So what happens if I have a heavier particle like this guy here? Where will it be? More to the inside or more to the outside? Inside. Let's see. Sure enough. So there's the spectrum. This would be a 1-to-1 ratio. Okay? And so I have these simple mass units here. Of course, we can do millions of a mass, actually. So you would have hydrogen. Hydrogen you would have as mass 1, is that right? There would be hydrogen, 1 proton. Mass 2, what could that be? Helium is mass usually helium. Helium 2 it could be. With no protons, kind of hard. H2. H2, or I can have a heavy hydrogen, it's called deuterium. It has 2 protons. One proton and 2 neutrons, I'm sorry. It has 1 proton and 2 neutrons. So what would be mass 3, for example? So I use this one, and I use one of those. Would that give me mass 3? What would that be called? Deuterium. That's deuterium, H3. Okay? Or I use helium 3. That's 1. Helium has 2 protons and 1 neutron. So it's 1 neutron missing. It's an isotope. So now let's see. What would be here? What would that be? Mass 12. Carbon 12. Mass 13. I'm listening? Carbon 13. Mass 14, 15, 16. What would that be? Oxygen 16. And what would that be? Can be oxygen 18, but what else? A compound? We dealt with it all the time. Water, exactly. Water, H2O 16, and oxygen 18. Now where would be H2O 18 be? Would be right here, at 20. So what would that be? That's 32. That's oxygen. Oxygen 16, 18 is 34. Oxygen 18 molecule is twice 18 is 36. And then we come to carbon. Carbon is 12. Oxygen 16 twice, of course, is 32 plus 12 is 44, 41, 42, 43, 44. And this is CO2. Now if I use carbon 13 and oxygen 16, it's 45. If I use carbon 13 and oxygen 18, what is it? Come on, wake up. 49, exactly. I don't have it here. 49 would be here. Good. Alrighty. So now we have these ratios. And you see here, I talked about this earlier, that these are weighted averages of the individual isotopes. Yes? Yes, go ahead. Yeah? I thank you for asking. I forgot to tell you. In this thing here, I made a different lengths to get all the graphics in there, all the writing in there. But that's a very valid question. I said, when I talked to this here, this was a ratio of 1-to-1. Remember that? So the height of the signal, how many you have in there, that gives you the relative amount to each other. Okay? So if I have a ratio of 2-to-1, that one signal should be this size, and the other one should be the double the size. Or 3-to-1, 3 times the size. That's a very good question. Thank you very much. Good. Good that you reminded me. So we have talked about this. It's a child's play for you. Now we come exactly to your question. We have a mass here, mass spectrum. There's mass 32, 34, and 36. And we have an equimolar mixture of oxygen, atomic isotopes. Equimolar. That means we have, which is the correct spectrum? This here, or this, but you need a little bit more. There's oxygen 16 and oxygen 18. Of course, in nature, they are not equimolar. That means the same number, large number. So you have oxygen 16 and oxygen 18, same number, very large statistical number, statistical distribution. So the nice thing is chemistry has these large numbers of atoms and molecules. It behaves perfectly statistically. When I give you a test here, I have this curve, which is a Gaussian curve. A couple of people have nothing, and a couple have more, and so there's a lot who are sort of in the middle, the average. There's some who have above average, and very a few superstars, okay? So you get this distribution, and the more you have, the smoother that curve is. And if you have a large number of sampling, then you have really statistically relevance. So if you have a medical experiment, and you have 10 patients, and you say 6 of these 10 patients did not get cancer, 4, or the cancer was cured of 6, and 4 not, it's meaningless. It's not statistical, okay? It reads well, but it's no statistical evidence whatsoever. A lot of this stuff is out in the literature, okay? That's why I need to know statistics a little bit. All right, so why don't you think about this and give me your answer? So this would be a ratio of 1 to 1 to 1. It's 1 to 2 to 1, 2 to 1 to 2. That's exactly the question I got asked. Let's do it in the middle. No, let's do it before. So now you're already doing chemical analysis. You analyze oxygen mixtures. Equimolar means the same number of mole. And the mole is a very large number. A million, billion, billion. That's 10 to the 24. A million, billion, billion. Billion is 10 to the 9th, twice is 10 to the 18th, and then a million is 10 to the 6th, so 10 to the 24. It's about a mole, a million, billion, billion. Okay, let's see what you got. Where's the rest of the people? You need to click in. We are not counting yet, but beginning Wednesday, you just got to make sure that you push the button. I'm not saying you don't have to have it right, but to be sure, push it right at the beginning that you don't forget. You can always revise your answer, okay? So we had 200 and 400 or something we had before, isn't it? 300 how many? 18. And now we have very few. Okay, have they left already, or did they give up already, or what? That's not statistically distributed. That is really evenly distributed, okay? So let me help you. Imagine we have a mole. I won't have a sack big enough to put that mole in. We have a mole of oxygen 16. These are red billiard balls. And oxygen 18, these are green billiard balls. And I have this immense sack here. So I take one out, the red one, oxygen 16. Now I grab in with the other hand. What's the probability that I have a green or the red one? What's the probability? 1 to 1, 50-50, okay? So I grab one. There's a red one. Oxygen 16, oxygen 16. I put this aside. Now I hold it still up. I have another one on the side. I put this up. I grab a green one. Oxygen 16, oxygen 18. Okay, I put this aside. Now I take a green one. That was oxygen 18, wasn't it? Yeah, oxygen 18. Now I have again a 50-50 chance. I grab in here, and I have a green one, oxygen 18, 18. Now I have the green one, grab again, and I have oxygen 16, 18. There's the answer, okay? Think about it again. Now I want you to discuss it. Introduce yourself to the person in front, the person behind, the person on your sides. Introduce yourself and discuss it. Vivid discussion about it. I love how you discussed it. So what is it? I explained it to you. All you had to, what I put on the side, you had to add it up. Okay, make sure you click in. You have 15 seconds left. Click in. Wednesday, we start counting. You get it? Participation points. Okay? Someone said, I don't want to really deal with this. How did you get that? Statistical distribution. So I had oxygen 16, oxygen 16, 1. Oxygen 16, oxygen 18. 1 oxygen 16, 18, 1 oxygen 16, 16. Now I have the green one. Oxygen 18, grab the oxygen 18, grab the other one, 18, 18. 1, 18, 18. Now I grab the other one, statistical distribution. I have a red one, oxygen 16, 18. How many 16, 18s do I have? 2. And how many 16, 16s do I have? And 18, 18s? So what's the ratio? 1 to 2 to 1. Okay, what would that have been? That would have been B. So now I will solve it for you. There it is, oxygen 16, oxygen 16, 18. See, watch it there, okay? But now we have one more 18, 16, and there it is. And I'm glad that I got to ask that question about the intensity, all right? So now we're going to burn hydrocarbon. You do that every day. In your car, you burn hydrocarbon. It's carbon and hydrogen. This is called hydrocarbon. They can have different lengths, different structure, but they are carbon and hydrogen. And if you burn them or combust them, they make oxygen. They use oxygen. The carbon grabs oxygen and makes CO2. That's our big problem. And the hydrogen grabs oxygen and makes what? Water. So the result of a combustion of hydrocarbon is CO2 and water. What mass is CO2? 44. What mass is water? 18. Okay, there it is. CO2, 18. And you get this kind of spectrum. You have a 2 to 1 ratio. I want to know which hydrocarbon is it. But first, I want to wake you up, okay? Please, we burn some hydrocarbon. One second. Let's burn some hydrocarbon. No, it's not going to be that loud. Karen has a way of doing this because when I do it, it goes right in the face of the students. Wow. Did you feel the heat in the back there? Did you feel the heat? Can you imagine the amount of energy that is there? That's how you drive your car. Okay? That's what happens in your car. Water and CO2 out the exhaust, and the little spark plug makes the hydrocarbon go with the oxygen that you have through your car intake shaft, or whatever it is. So now you are ready, awake and ready to answer that question. What? That's okay. Okay, let me give you this here. I forgot to give you the overview here. Anyhow, what's happening here? The computer is from 1860 or something. Huh? Can you believe this? Yeah, I mean, Cal is not doing so well money-wise. I can't believe this. Look at this. Okay, never mind. So, now let's answer that question quickly. What is the spectrum? I still have 5 minutes. Oh, there's one noise, this thing here. It's a piece of not good equipment. I can't believe this. It's frozen. No, it's not. There it is, okay. So it makes carbon dioxide and water. That's the important part that you need to know. Now, you're going to ask yourself, how much carbon dioxide can you make here, and how much water can you make out of this? You need to know the formula of carbon dioxide and water, though. That's one of the conditions. Don't forget to click in. Okay, we have still 3 minutes. We're going to solve that whole thing and get it over with. And move on to next time. There's people missing. Come on. Let's get with the program here, please. I don't record. I care if it's right or wrong, but I need a recording. You don't get points deducted if it's wrong, okay? You get participation points. People have not gotten it. So, How many carbon can I make here? Carbon dioxide out of this with oxygen. 1 CO2. How many waters can I make here? 2. What would be the ratio of carbon dioxide to water? 1 to 2. Is this 1 to 2? No. So now you need to go through this here and see if you get this ratio, and then you get the right answer. All right? I give you 1 minute. Discuss it with each other. 1 minute. Make sure that you click in. I stop it at 30 seconds. $30 seconds left. There must be an F the answer, yeah? F the answer. Okay, 7 seconds left. Click in. 2, 1. Is this your final answer? Okay. These computers, I think they're totally overloaded probably. Okay, very good, very good. Now let me give you the solution for it, and then we can go home, or wherever you're going to go. So this is methane is 1 carbon, 4 hydrogen, makes 1 CO2, 4 hydrogen makes 2 water. All right, there you go. That's a 2 to 1 water to carbon dioxide ratio, 2 to 1. Ethylene makes 2 carbon dioxide and 4 H2 waters. What ratio is that? 1 to 1. That was not what I asked. C2H2 makes 2 carbon dioxide and 1 water because you have only 2 H's, so it makes H2O. 1 and 2 CO2. It's a ratio of 1 to 2, and the answer was acetylene. And with this, I see you on Monday.